The strategies that we already developed for indeterminate forms apply to limits at infinity as well. Pause the video and try to evaluate each of these limits as x goes to infinity. Also consider whether the limit as x goes to minus infinity is the same or not. When x goes to infinity, the exponent here, 1 over x, goes to 0, so we get e to the 0, which is just 1. What about the limit as x goes to minus infinity? 1 over x still goes to 0, so we still get e to the 0, which is 1. In the second limit, we have to consider what the absolute value of x means here. Since x goes to plus infinity, we're really thinking about positive large values of x, so the absolute value of x is just x, and we get 3. But when x is going to minus infinity, the absolute value of x is minus x, so we're getting 1. The third limit is tricky. Even though this is of the form infinity minus infinity, we can still be inspired by a strategy that we had previously used for limits of the form 0 over 0, which is multiplying by the conjugate. And now, when we multiply on top, the difference of squares is x squared plus 1 minus x squared, which is just 1. Now, as x goes to infinity, the denominator is clearly going to infinity, so we get 0. How does this change when x goes to minus infinity? It's a little bit subtle, and as most subtle things with limits, it has to do with signs. When x goes to minus infinity, the square root of x squared plus 1 is still positive. All square roots are positive. But minus x is now also positive, because it's minus a negative number. So we're really getting a sum of two big positive things. It's not an indeterminate form when you add positive infinity to positive infinity. You just get positive infinity. In the last limit, we use our familiar strategy of log rules. And once you do that, the inside of the natural log function is an indeterminate form infinity over infinity, and we can use our old strategy of factoring to finally get the natural log of something that's growing to plus infinity. That limit is plus infinity. On the other hand, when we consider the limit to minus infinity, it's not that we get a different number, we get nonsense. While the natural log of x squared plus 1 makes good sense, the natural log of x minus 1 is undefined, because x is a big negative number, so x minus 1 is also negative, and you can't take the natural log of a negative number. There is one new important strategy. Consider the limit here. From our old toolbox, the only thing we can really do with a rational function is try factoring. But this numerator cannot be factored. So what can we do? If we divide top and bottom by x squared, we distribute that division to each term, and in the numerator we get 1 and something that goes to 0. In the denominator we get 2 and something that goes to 0. So the limit is just 1/2. The general strategy is to divide the top and bottom by the fastest growing term in the denominator. For polynomials, that's just the lead term. So here for this example, the lead term in the denominator is still x squared, and when we divide through then, in the numerator, we still have some term that's growing, the x term. But the denominator is not growing anymore. It's got that constant term, which came from dividing x squared by itself, and then it has other terms that are shrinking. Now when we use informal substitution here, we see that this limit goes to minus infinity. The book sums up the result of this strategy for rational functions in Theorem 2, and there are many examples of this kind. But this is actually a much more general strategy. For example, we could do a limit like this, where the top and the bottom of the fraction are not polynomials, but they have fractional exponents. Now to decide what the leading term on the bottom is, you have to compare these exponents and see that 4/3 is less than 3/2. And then when we divide top and bottom by x to the 3/2, we'll have to subtract fractions. Once you do that, you'll have a constant in the denominator, and everything else here has x raised to a negative power, So it goes to 0 as x goes to infinity, and the overall limit is just 0. These 3 examples can all be computed using the same strategy, but each one of them is a little bit subtle. Pause the video and try to compute them. In the first limit, we have to decide how quickly this square root term is growing. In general, the square root of a polynomial grows roughly the same speed as the square root of its leading term, so this one is growing linearly. Hence, we're going to want to divide top and bottom by x. When you distribute this through, it's clear that you should get 5 on top and that the minus 4x becomes minus 4. But what happens to that square root term? We'd like to rewrite x as the square root of something, so we can move it inside the square root and divide as normal. X is almost the square root of x squared, but not quite. The square root of x squared is always positive. It's the absolute value of x. When x is going to minus infinity, we think about x as a large negative number. So we need a minus sign in order to make this work. Then when you divide, you don't get the square root of 9 plus 1 over x, you get the negative of it. Now when x goes to minus infinity, the 1 over x disappears, and we get negative 5/7. Think to yourself about how this limit would be different if x was going to positive infinity. Now, in the second example, we have to think about how these exponential functions will grow or shrink as x goes to infinity. When we raise e to a bigger and bigger positive number, it grows. So here, e to the 2x is growing. But when you raise e to a bigger and bigger negative number, it shrinks. Hence, the e to the 2x here is the leading term, and that's what we want to divide by. Use the exponential rules on your pre-calculus fact sheet to distribute. You should get this. Now, in the remaining exponential functions, e is being raised to a larger and larger negative number, so those terms will go to 0, and you just get 1/3. What happens when we take the limit of the same thing, but as x goes to minus infinity? Well, now e to the 2x is getting a larger and larger negative exponent, so it will shrink, while e to the minus 3x is getting a larger and larger positive exponent, so it will grow. That means the leading term here is actually e to the minus 3x. When you distribute this through, you should get this. Again, all the remaining exponential terms will vanish when we take the limit, and since there's a constant in the denominator, in the limit we'll get 0 divided by something that's not 0, so the overall limit will be 0. Please go on to the next video where we'll discuss the squeeze theorem at infinity.